Hi, this is Dr. Vev, and I'm here to talk about units and dimensions. If you were to ask somebody what the main difference between a mathematician and a physicist is, there are many differences, of course, but the one thing that comes to mind to anybody is that we care about units. We deeply care about units. In fact, many a time we are guided by units and dimensions, even at our research level, in determining if our approach is correct or not. Oftentimes, if the dimensions are not correct, then we know that the physics, however fancy, and the mathematics, however deep, is simply wrong. So, as physicists, we must strive to understand the nature of units. All quantities are measured quantities in physics. In UP1, especially in UP1, there are three main quantities: the unit of length, which I indicate as that. Now that stands for the dimensions of length. And I also use it for the SI units. So it serves a double purpose. So when sometimes I can write the units of length are meters, because in SI units, meters or m are the units of length. Similarly, the dimensions of mass are written like that. And the SI units for mass is kilogram, written kg. And finally, the unit t is the dimensions of time. And it's defined as seconds. Now you can look up the way these basic units are defined in terms of fundamental constants of nature and so on in various websites, including the NIST website, which is highly recommended, National Institute of Standards. So the NIST website has listings. So just Google that and you'll find the NIST website. So anyway, these are the three main units for UP1. In UP2, you can add the units of magnetic field and the unit of charge and a few others. In UP1 or University Physics 1, we're only going to have these three. It means that every quantity we're going to study in UP1 is going to be made up of a combination of these basic quantities. For example, speed, velocity. So suppose you say the car is going at 60 miles an hour. You can clearly see miles means a distance L, dimensions of L, and per means just a division sign, and hour is the dimension of time. So the units of V are going to be L over T, written as LT minus 1. And now you notice that I write the dimensions of L as just L, because I'm more concerned with the units of V here than with L. So I occasionally omit the parenthesis and simply write it as LT minus 1. Suppose we don't know a formula. One of the great advantages of this method of dimensional analysis, or looking at dimensions of certain quantities and guessing the nature of a formula. So let's say you want to find, let's say you want to deduce the period of a pendulum. Now everybody knows what a pendulum is. You just tie a string to the ceiling or some support stand on one side, and then a heavy mass on the other side. This mass is considered to be a point mass for this exercise, You have the length L of the string. When we go to simple harmonic motion, I'll define this length more carefully, but right now it's just some length. And of course we have the acceleration due to gravity. Acceleration in UP1 is indicated by a double shafted arrow. So that's the acceleration due to gravity of the Earth, which I'll call as G sub E. So those are the ingredients, and from this you need to figure out how long it takes for the bob to move back and forth once. I'm not going to do this too many times or you'll fall asleep, but the time required to go once back and forth is known as the period. Confusingly, period T has got the same designation as the dimensions of time, but maybe to avoid that, I'll write this as little t for now. Maybe even call it TP for the period of the pendulum, so as not to confuse with the capital T over here. Now, what can we say about the period of the pendulum? Well, you may think that if you have a heavier mass, it'll swing faster. So that's one kind of thought you may have. It turns out it's wrong, but actually, amazingly, the mathematics is going to prove it. So let's say for now, we don't know much about anything about this subject. So we assume that the period of the pendulum is going to be some constant C, which can be some number, mass to the power A, where A is a constant we have to determine. It may also depend on length. The longer the string, the more leisurely it may swing. So L to the power B. And by the way, you can even test out these things by simply tying a stone to a piece of thread and seeing the effect of length and mass. In fact, there's a lab we'll be doing on that very subject. We'll be using regular weights and not stones. And then also it may depend on the planet, because if you were in Jupiter or something, it'll oscillate really fast, and if you're on the moon, it'll oscillate very slowly. So it should depend on the gravity, acceleration due to gravity, and I won't put E because it can be any planet, to the power C, and maybe I'll call this C1, the constant C1. So C1 is some constant. So we're going to assume that the pendulum's period is of that form. Now, how can we use the idea of dimensions to solve for A, B, and C? Amazingly, this will tell us the period of the pendulum up to a constant, because this constant C1 has no dimensions. If you don't have any dimensions, this method is useless in determining that quantity. So let's take the dimensions on both sides. So dimensions of T, Tp, are going to be the dimensions of C1 times the dimensions of M to the power A, dimensions of L to the power B, dimensions of gravity to the power C. Now, the acceleration A is measured in meters per second squared. It tells us how fast the speed is changing. So it tells us you have speed, which is meters per second. How fast that is changing with time is meters per second, and that's how you get meters per second squared. So you need to know a few basic things like that in order to use dimensional analysis efficiently. Okay, that is where we are right now. Let us try to solve this. On the left side, the dimensions of t are just t, time. Now, just because we're going to compare very soon, I'm also going to write t to the power 1 here. I have no mass on the left side, so I'm going to write m to the power 0. And I have no length on the left side, so I'm going to write L to the power 0 also. On the right side, the units of a constant, well, constant has no units, so I'll just put the number 1 there. And then I have units of mass to the power A, units of length to the power B, and G is meters per second squared. So in fact, the units of acceleration are Lt to the minus 2. I'm writing it like that, bringing L over t squared, writing it as Lt to the minus 2. So that's going to be Lt to the minus 2 to the power C. At this point, what I'm going to do is use the rules of powers. So on the left side, I still continue to have m to the 0, l to the 0, t to the 1, while on the right side I have m to the a, l to the b plus c, because you have l to the b times l to the c, and that's going to be l to the b plus c. And then I'm going to get t to the minus 2c over here. Now all I have to do is compare the powers on both sides. This immediately tells us that a is 0 or does not depend on mass. And this is actually very startling because I have not done any experiment. I have not taken a bunch of different bobs and measured it, the period with the L remaining the same but the mass changing. You'll be doing that experiment in the class, but I have not done that. Mathematics is telling me that A should be 0 on purely dimensional grounds. So this is a very powerful method. The next equation is 0 equals b plus c, because the power of length has to be equal on both sides. Well, this just tells us that b equals minus c. So we'll save that. Here I get 1 equals negative 2c. I always like to put the algebraic variables on the left side. That's why I'm writing it as negative 2c equals 1. Well, this gives us c equals negative half immediately. Well, if c equals negative half and b plus c is 0, it means that b must be equal to positive half. So in this manner, I have actually solved the problem. The period of a pendulum, Tp, is going to be some constant c1, which I've still not determined. It's not going to have any power, any dependence on mass, m to the 0, and then it's going to have L to the b, which means L to the half, times g to the minus half. Or we can say that period of pendulum is equal to c1, m to the 0 is just 1, and that's L over g square root of. So that's the formula we seek. Pretty astounding, don't you think? What we can do with this, even though we don't know the constant up front, it'll turn out to be 2 pi when we do the actual physics rigorously later in the course around week 10. This constant will turn out to be 2 pi, but right now we have no way of knowing that. But what we can do with this method, even if you don't know the constant, you can compare, you can ratios. For example, if I can write Tp1 over Tp2. When I do the ratios, the constant is going to cancel out. So I'm just going to get square root of L1 over L2 times the square root of G2 over G1. And this enables us to compare the periods for different lengths of pendula and also different planets. For example, if you keep the lengths the same and you go to the moon, then you can find, knowing the acceleration of the moon compared to the acceleration of the Earth, say the acceleration on the moon is 1/6 the acceleration of the Earth. So G2 is 1/6 G1. That's the elementary fact you learn in high school. And let's suppose that L1 equals L2. So if you take a pendulum to the moon, so T Earth over T moon is just going to be the square root of 1/6. So this tells us that the period on moon is going to be bigger. If you solve this, I get root 6 times TE, which is expected, because if gravity is weak, then the pendulum is going to swing slowly. So one of the advantages of dimensional analysis is it facilitates comparisons of these ratios, because that eliminates the fact that we cannot find C1. So I hope this video gave you a brief taste of why dimensions are so important in physics, and how, using just dimensional analysis, we can try to find out deep hidden truths about the way the world works. Now, this method I've taught you is actually a very important method, and engineers in particular take entire courses where you analyze the dimensions. For engineers, this is very important because you can build a scale model of a ship or a satellite and do experiments on that, and by seeing how the dimensions scale up or scale down, you can then predict how a full-scale object, like a big ship and an actual satellite, would behave based on those little experiments you did on the models. So in engineering and of course in physics, this method of dimensions and analyzing dimensions and always worrying about if quantity has got dimensions is pretty important.